First of all, I would like all of you to join my webinar presentation and welcome you here. So my study is focused on panel data analysis of the congestion at selected locks on the upper Mississippi River. Let's move to the introduction section. So the possibility and reliability of waterway navigation in the upper Mississippi River are created with a sequence of 29 lock and dam facilities. We have a series of level pools which are created with dams, and there are establishment of locks which permit the transportation. The vessels to pass through the dams. The vessels are defined as anything like boats, barges, ships, etc. The problem with locks in the upper Mississippi River system are most of them are obsolete, and they cannot keep in touch with the modern day commercial navigation demands, which means we will have a significant amount of delay at locks at upper Mississippi River. So the objective of this study is to analyze the probable factors that influence lock congestion at selected upper Mississippi River locks. Let's define some terminology related to our study. Lock is defined as a facility containing one or more enclosed chambers and situated at a canal or dam across the waterway, and each lock has gates at each end for raising or lowering the vessels by admitting or releasing water. That's how a lock works. Lock closure is simply defined as a situation where the lock is unable to perform the locking activity. So the US Army Corps of Engineers has identified 4 categories of lock closures. They may be closed due to weather conditions, due to mechanical problems in the vessels, some vessel characteristics, and some miscellaneous factors. Average lock processing time is defined as the total processing time of all vessels divided by the number of total vessels. Similarly, average lock delay time, which is the dependent variable in our study, in our whole analysis, is the total delay time of all vessels divided by the number of total vessels. So the methodology, the monthly data, we have a monthly data of 11 years from 2004 to 2014, and it's since monthly data we have 132 time periods with a panel structure of 16 locks. 16 locks means we are selecting 16 out of 29 locks on the upper Mississippi River. So the usual procedure with the panel data structure is to either implement the standard fixed effects or random effects estimation approach, where we have lock specific units as individually specific units, and we have time period specific units of 132 periods, which is an advancement on pooled ordinary least square estimation approach. But the thing is, the core purpose of our study is to capture the distinct seasonality and annual time period effects rather than aggregating year and month together to get 132 time period effects. So this would give rise to the least square dummy variable estimation approach. However, LSDB is one way of estimating fixed effects approach, but the only difference here is in the LSDB estimation approach we would include only 11 annual time period fixed effects, I should say only effects, compared to including 132 combined time period effects in the usual fixed effect estimation approach. These are some of the estimation approaches for our analysis. So the usual pooled OLS estimation is the one where we just ignore the panel framework of the data. We just don't include any log specific effects and time period specific effects. So the usual model looks like this, where EIT is the usual idiosyncratic disturbance, which is assumed to be identically and independently distributed with mean 0 and variance sigma square as usual. YIT is our dependent variable, average delay time, and XSide is the matrix of explanatory variables, which includes average processing time and the frequency of unscheduled closes by category, mechanical, order, vessel, and weather. The main assumption for consistently estimating pooled OLS here is the error terms are uncorrelated with the explanatory variables for that time period only. That means we don't allow contemporaneous correlation across error and explanatory variables. So the another approach, the standard approach, is fixed effects, or we call it within estimation approach. So what we assume with this approach is that the individual effects are time invariant. I mean the variance, we have constant variance of individual effects, and thus they are considered a part of the intercept. Since they are considered a part of the intercept, they can be allowed to be correlated with other regressors. Uh, two-way random, it should be two-way fixed effect model would consider including time period fixed effects. Uh, means constant variance across time together with individual fixed effect. So we can see the model look like this, where we included mu I and theta t. So mu I are log specific, simply individual specific effects, and theta t are time period specific effects. As usual, EIT, XIT we already defined, YIT is the dependent variable, and the main assumption here for consistent estimation of like fixed effect estimation would be there should be no correlation across error terms and explanatory variables for all time periods. Not only contemporaneous error correlation, but it rules out any kind of correlation between error and explanatory variables across all time periods. So the another estimation approach is random effect estimation approach. The main difference here is we still have individual effect and time period effects for two-way random effect estimation, and the main assumption here is that the individual and time period effects are not correlated with the regressors. That means they can be allowed into the composite error term. And the another thing is the individual effects and time period effects are not fixed. They are random. We can call them as individual specific random heterogeneity and time period specific random heterogeneity. So the variance specific to groups and variance specific to time periods will include into the composite error term. We can write the random effect estimation with the following specification, where mu y and theta t are already described as in the fixed effect estimation approach. The main assumption, as I already stated, would be that mu I and theta t are assumed to be uncorrelated with the matrix of explanatory variables. We also need the previous assumption of no error correlation with explanatory variables for all time periods, as we did in the fixed effect estimation approach. From the literature, we found that log delay is not only associated with various lockage and vessel characteristics, but is also influenced by some seasonal factors. So Though we have the LSTV estimation approach as one of the kinds of fixed effect estimation, like within estimation, but the one we are trying to use here is the one which captures all the seasonality and annual and time period effects, including log specific effects, by assigning log, month, and year specific dummy variables. So the specification looks like this, where we have included all the dummies and we dropped out the dummies for the log 11, month of January, and the base year 2004. Dropping those dummies allows us to get rid of the issue of multicollinearity. Otherwise, we will have multicollinearity if we include them. So the only assumption needed is that the error terms are uncorrelated with the explanatory variables for all time periods, as we did for the random effect and fixed effect estimation approach. We can define the dummy variables as, for example, for log 12, it takes a value of 1 if the delay is associated with log 12, otherwise 0, and so on. We proceed the estimation using the software R. So we need to estimate all of these four models like LSTB, full OLS, fixed effect, and random effect to make sure and get specification tests that follow to best describe which estimation is appropriate for our data. So we have the estimation and we have the following outputs from pooled OLS, two-way fixed effect, and two-way random effect estimation. We can see the intercept term from two-way fixed effect is dropped because the fixed effect estimation or any time invariant characteristics which are included, which goes to the intercept term, will be dropped naturally. We can see the processing time is highly significant, and since the number is in hours, if we want it in minutes, we just have to multiply with 60. So processing time is highly significant, and we can see the closures due to racial and weather characteristics are also significant. But we can't say mechanical and other have any significance on average log delay time. So we have variance for the composite error term, variance for the individual or log specific effects, and variance for the time period specific effects in our two-way random effect estimation. Similarly, we have the specification test, and we have LM test for random effect estimation, two-way fixed effect test, and we have Hausman test. These will be described in the coming slide, and all of them are significant. We can see them from the output table. The purpose of Lagrange multiplier test, Bruce-Pagan Lagrange multiplier test, is to check whether we have random effects, whether we have individual and time period random effects. So what we mean by random effects is like the individual or time period fixed effect. Sorry, it should be effects only. Individual or time period effects are not fixed, they are random. That means they vary across time or across individual. So the null hypothesis is there are no variances in individual or time period fixed effect. So an LMS statistic of 492.71 rejects null hypothesis, and we conclude that we do have random effects in our data. Similarly, F-test is done to check if we have just individual and time period fixed effect in the data. A computed statistic with a value which is very low, 3.91, because we lose a lot of degrees of freedom, including all those dummy variables, is still significant. That means we can say we still have fixed effects in our data. So finally, we have to do Hosmer test to determine between random effect and fixed effect estimation. The null hypothesis of Hosmer test would be there the individual and time period specific effects are uncorrelated with the regressors. By the way, this is the same assumption we need for consistent estimation of random effect. A failure to reject this null hypothesis would mean that we go forward with random effect estimation. Here, the Hausman test returns a chi-square statistic of 7.8, which is significant at 0.01 levels. This implies that we reject the null hypothesis and conclude that fixed effect estimation is appropriate compared to random effect estimation, though we have both fixed and random effects in our model. Since we found that two-way fixed effect estimation approach better describes the data than the two-way random effect estimation, we can proceed with forms of fixed effect estimation. Here we proceed with LSTB estimation. Since LSTB estimation is one of the kinds of fixed effect estimation, but the thing is, like we already mentioned, that we want the annual and monthly fixed effects in the data to be estimated rather than the aggregated time period fixed effect along with individual or log specific effects. So these allow us to include LSTB estimation. We have the LSTB regression outputs in the upcoming slide, and from the outputs we can see that average processing hours and frequency of on schedule weather closures have statistically significant impacts at all levels of significance on the dependent variable. By converting it into minutes, we can see that an additional hour increase in the processing time would increase the log delay at any log by approximately 24 minutes. Though significant, the weather impact is very low compared to what we expected. The unscheduled vessel closure, the frequency of unscheduled vessel closure has statistically significant impact at 0.01 level, and with an approximate 10 minutes increase in delay with an additional closure due to vessels. So these are outputs I was talking about. Here I have listed only the important or significant coefficients with their outputs because we don't want to include all those coefficients on log, month and year dummies. So these are the important or most significant outcomes we have from the LSTB regression. Let's proceed with interpretation of some of these outputs. So as usual, the log, month and year specific dummies would explain a special seasonal and annual fixed effect. Similarly, we can see the logs 25, 26 and 27 have significantly higher average delays compared to the log 11, which is our reference log, with 48, 35 and 115 minutes increased delay respectively. Similarly, for the coefficients on month, April, May, June and August, that shows significant delays, higher delays at 0.05 levels compared to January, with almost 25 minutes increased delay during month of April and almost 30 minutes increased delay during month of May, June and August compared to the reference month of January. For the month of July, the increased delay, the significantly higher increased delay was observed at all levels of significance with almost 66 minutes increased delay. Log delay for the month of November found to be statistically significant at 0.01 levels with almost 32 minutes increased delay compared to the a reference month of January. Similarly, for the year dummies, we can see that for the year 2012, 13 and 14, we have statistical significance at all levels, showing an approximate 77, 44, 45 and 70 minutes increased delay respectively compared to the base year 2004. So what we conclude from the regression output from LSTB estimation approach, the average processing hours and frequency of unscheduled closures due to weather conditions and vessel characteristics showed significant impact on the average delay, which the direction of the impact was as expected. Uh, in fact, we expect all of the unscheduled closures, whether it is due to weather, vessel, mechanical, or any other kind, should have significant impact on congestion, but that doesn't happen in our study. So the coefficients on log 25, 26 and 27 showed significantly higher average delays compared to the log 11, which are consistent with our expectations, as they happen to be the lowermost logs on the upper Mississippi River with a significant southbound traffic all year. The low coefficient on the months of January, February, March, and December, the winter months, are actually omitted from the LSTB output table, but this suggests that the winter conditions might affect the waterway navigation due to the low level of water or even the freezing conditions. That means we have lower delays at log. Similarly, for the year specific dummies, what we got, that showed a considerable increased delay compared to the base year 2004. These delays would imply that there is ever increasing waterway traffic in the recent years compared to the previous years. That's all. That's all what I have for the conclusion section. That's all I have for the whole study. So these are some of the references. Any suggestions and comments are always welcome. You can always email me. Thank you for listening me.